fixed it. All right. We'll give this a shot. So I'm using the desktop here as a means of recording. I'm going to try this a little differently. One of the advantages, I think, is that it uses these microphones, which I think are far better than the one that I have clipped onto my lapel. And plus, we can pick up you all. So let's see. So looks like it's recording. All right. Okay, so let's get started. We'll try this out and see if it works today. So I just want to make sure everybody's clear on the logistics. We have sort of an odd introductory homework schedule because of the delays in the manual. So right now, I think I have, I don't want to say a typo here, but this probably needs to be updated, but at least I had updated it on my computer upstairs, and then of course it didn't update. That is a tally mark mistake. So homework 1.1 here, I'll fix that now. So let's make sure we're all clear on this. So homework 1.1 is graded, and the solution's posted. Now homework 2.1, I believe, is currently being graded. And homework 1.2 and 2.2 are going to be due Monday. Yeah, that's right. So yeah, okay. What we're going to do today is continue our discussion of net area, but we're going to take this formula and we're going to complicate it a little bit today. So I want to go back to this. I didn't write this in the slides in the last in the last lecture because we sort of organically derived it, and I think there's a little bit more inherent understanding that the net area formula before was the gross area minus, and all we had was this concept that it was just the area lost due to the presence of bolt holes. Well, now we know that there is a means to compute that, and it is the sum of the hole diameters times the thicknesses. And so, for example, and I like sort of putting it in this format because the thickness and whatnot can change dependent upon the cross-section. One of the homework problems, you had holes going through different plates, right? So you had some going through the flange, some going through the web. And so writing some super descriptive formula probably would make it more complicated than it really needs to be. In fact, in other words, if you can use some intuition, I think that the math is a little bit more straightforward. But I propose to you that this formula is not enough, that there's something missing right here, okay? And what's missing there is the effect of staggering the bolt holes, okay? Now, we talked last time about why you would do that, why you would use a staggered connection. So why would you? You might know why. We talked about this last time. Why would we use a staggered bolt arrangement?
It raises your net area.
It raises your net area. And why is that valuable? Why do we care about that? Well, if we increase the net area, what do you think that does to the strength? It increases it. So from a design standpoint, I can get more capacity out of the same member without changing the size of the member, without increasing the number of bolts. I get increased capacity for no extra charge. Okay? So, but we have to be able to account for that. So I propose that this formula is incomplete. That what it should be is the gross area minus the area lost due to the presence of bolt holes plus something. We have to add something for when we have staggered bolt arrangements. Now I'm going to go ahead and tell you right now what this something is. We're going to add any stagger factors. That's what's missing. Okay? And I'm sure the $64,000 question is, so what's a stagger factor? So that's going to kind of be the purpose of our discussion today, is to look at staggered arrangements. So Again, to be clear, parallel grid-like bolt arrangements like this, we can use this formula. I just propose our stagger factors are 0. Okay? So a parallel bolt arrangement is pretty common, arguably the most common, but we can also deal with staggered bolt arrangements like we see here on the bottom. And as I've said, the goal is to increase the net area of the section. Increase net area, more capacity, don't have to spend more money on steel. Okay, so a couple of things. Whenever you're dealing with staggered bolt arrangements, there are two, added complications. Okay? So, first off, how do we account for increased area along the failure paths? Well, that's what a stagger factor does. Okay? But the other one is, how do we account for multiple possible failure paths? For example, let's take this connection here. Okay, I'll draw over here on the right. So, let me see if I can turn on my pen here. So, it doesn't like me. So, for example, let's take a look at this connection here on the right. One potential failure path is like that. How many bolt holes would I subtract? 2. Okay, let me use another color here. Here's another potential failure path. Now how many bolt holes am I subtracting? 3, but I've got one path that's diagonal, right? So I got to be able to account for that. Here's another one. Okay? Let's get another color out. How about this one? How about that? That is yet another potential failure path. Okay? This has 4 bolt holes, but then there are also 2 staggered paths that we would need to account for. Does everybody kind of get what I'm talking about? Now, before we talked about, I had mentioned this term lead line of bolts. Okay? So, before it didn't really matter, now it kind of does. So let me sort of introduce this. So the lead line of bolts, if you want the technical definition, the lead line of bolts is the collection of bolts such that if the member were to fracture along those paths, all of the bolts would remain intact. So let's kind of look at this bolt pattern over here. So I'm grabbing the member, and I'm taking the member, and I'm yanking it. You can look at this path over here, it doesn't matter. Okay? If I were to fracture the member, sever the member in half along, one of these bolts, or if we wanted to get crazy, here's another potential path. We could also have this path. Hold on. Here's another path for you. It doesn't matter which path that we're looking at. If we're looking at the red one, the blue one, the green one, the purple one, they keep the bolts intact. So if I take here and I yank, if I fracture on this path, I leave my bolts intact. Okay? If I fracture along this path, I leave my bolts intact. Now, let's just for the sake of discussion, let me ask you a question. So, let's say that I fracture along that path. Okay? So I'm grabbing the member, I'm yanking it, and the plate fractures right here. The only way to separate this member from the connection are if these 5 bolts also shear in half. Does that make sense? Everybody okay with that? So I propose that these bolts constitute the bolts that are on the lead line. Now, if you want a simple way of looking at it, imagine that this was that this member was turned up like this, and you were standing here. If you looked, which bolts are you going to see? Those bolts. Does that make sense? Those are the bolts that are on the lead line. It never really affected area computations for parallel connections Because if you go back to, let's say, this member, okay, how does the net area computation change if you're looking at this path versus like this path? It's still the same formula, right? Which is why it didn't really matter before, but now it kind of matters to make sure that we're all understanding the, the lead line. Does that make sense? Everybody okay with that? Okay. Let me erase all this ink here. Okay, so let's consider this connection, okay? So what I've done here for this, and this is very typical in steel design, is that we'll lay out the connection and then we'll use these letters, if you will, to sort of identify the potential failure paths. I want to see if you all can help me identify all of the potential paths along this cross-section. We'll talk about some of them and see whether or not they're realistic, whether they're not, how the formulas would change, etc. So I want to look at this particular connection. Now, one of the things I highlighted before was the presence of the break line. So here is the break line right here, okay? So that means the rest of the member is out here. I'm grabbing the member and I'm yanking it from here. So if this is the break line, that means that the lead line's coming from this way, that these are the lead bolts, not these. Does that make sense? So based on this naming convention, I want somebody to identify a potential failure path. Somebody call one out. Doesn't matter, anybody.
A, C, D, E, F.
A, C, D, E, F. Okay.
I didn't get that. Could you try again?
Nope.
A, C, D. I'm kidding. 100% correct. Okay? So maybe we'll draw that out here. Now, why didn't you do B, C, D, E, F? Why not that one? I'm asking everybody else. Like, that's the right answer, but why wouldn't you say B, C, D, E, F? I'm just curious.
It's not symmetric.
Well, the symmetrical, that's not really a consideration here, because here's my point. These staggered distances might not be symmetric. There are real instances where that's the case. I'm going to talk about that here in a little bit. But why not B, C, D, E, F?
If you're going from B to C, there's more like tensile strength added.
Exactly. Like if we're taking this piece of steel and we're yanking on it, where is the path at which it is most likely to fracture? It is most likely to fracture just this way. For it failing along that path, that doesn't really make sense. That would mean there was more area that the load would have to fracture through. Does that make sense? So ultimately, we're going towards like paths of least resistance. So that's why A, C, D, E, F is a viable path, but B, C, D, E, F is not. Is everybody okay with that? So give me another one.
A, C, E, F.
A, C, what, say it again?
Oh, wait.
Now, hold on. Say it, now, let's stick with that. You said A, C, E, F, but then you said hold on. Why'd you say hold on?
Because D would also have to break.
Exactly, yeah. So we're only going to consider paths through the lead line. So this is not a viable path because we would have to fracture through that front bolt to separate the member from the connection. Does that make sense? So that's not a viable one. So somebody give me another one. Let's try another one.
B, D, E, F.
All right, B, D, E, F. Okay? So that's going to look, let's see, like this one. Is that a viable path? Is there another similar viable path?
A, C, D, G.
A, C, D, G. Now what I'm going to do is sort of list those together. Why am I listing them together?
Because they're the mirror of one another.
They're exactly so regardless of the math, like ignore the math, they're basically the same path, right? They're just mirror images of one another. Now, the only reason that they are the same path is because this is in fact a symmetric connection. There are examples and there are cases where that isn't going to happen, okay? In in those instances, these would be treated separately, okay? And to be clear, what I'm saying is they would be treated separately if you had different distances here than you did here. And there are instances where that could happen realistically. Specifically, if you want to know what I'm talking about, I'm talking about angles where the stagger crosses the legs. You can have different stagger distances. Make sense? Are we missing one? BDG. There you go. Exactly right. Oh, there it is. There it is. I was having a hard time finding my cursor there. Yeah, BDG. Make sense? Okay. All right. Any questions about this? Like being able to identify them? Because we're going to do this here in a little bit. All right. Now I need to take a step back and talk a little bit about this. This is the equation for a stagger factor. Okay? Now, the stagger factor is defined as S squared over 4G divided by the thickness. Okay? Now, I'm going to first talk about the math because I see everybody saw the formula. Like, oh, I got to take my little pencil and write that down. So let's talk about the math. Okay? So the equation for a stagger factor is S squared over 4G. S is the longitudinal spacing. S is parallel to the applied load. G is the transverse spacing. It is perpendicular to the applied load. Okay? So if you're yanking on a member, S is measured along the member. G is perpendicular to the axis of the member. And T is the thickness. Now, if everything's measured in inches, let's talk about the math. If everything's measured in inches, what is the units of a stagger factor? S squared T over 4G. It's in square inches, right? So, look at my formula over here. My formula over here says I have the gross area in square inches minus whole areas in square inches plus stagger factor. So it makes sense that the stagger factor be in square inches, right? It's got to be. Now, if you open up the code in your AISC 15th edition steel construction manual, it does not say S squared over 4G times the thickness. It just says S squared over 4G. Because the way the code is written, it stipulates that you add S squared over 4G to each path. But then you take the paths and multiply them by the thickness. So that's why I've got the thickness in there. All right. Everybody okay with this? With this formula? We'll talk about some specifics about the formula that you need to understand here in a little bit. Does everybody understand? Okay with the concept so far? Now, we need to take a step back, and we need to talk about the difference between mechanistic expressions and empirical expressions. How many of you ever had a class that deals with empirical expressions before? If you haven't, you're about to real quick. Did you take concrete design? You took concrete design, right? You did or did not?
I did.
You did. So concrete design is full of them. 0.85 FC prime and 57,000 square root of FC prime and all the shear equations, all sorts of empirical expressions. Where do you think all those, fluid equations come from for open channel flow and things like that? What about geotech? The oodles of empirical expressions in there. What do I mean when I say empirical expressions? What am I talking about?
Applies to any scenario.
What's that?
Applies to any scenario.
Not quite. Not quite.
It's not based completely off of like science. It's where they took a bunch of like data points and created like a lot of best fit for it.
There you go. That's what we're talking about. Here's the thing. What we are talking about is stress distributions across plates with intricate geometry, if you will. I mean, if you just take a single plate and drill a hole through it and yank on it, the resulting stresses that you get are weird right there around the connection. And unfortunately, we got to deal with it. Like, we can't just make that problem go away because it's hard and we don't want to deal with it. It's there and we have to. So a lot of times in engineering, I mean, don't get me wrong, we have, principles of statics, we have Bernoulli's equations, and all sorts of mathematically, rigorously defined expressions that, make the world go around, if you will. But sometimes engineers have problems that are just tough, that we have to deal with, but actually trying to derive a closed form solution or do some super rigorous analysis for every routine design becomes cumbersome. So what we do is we develop empirical expressions. Stagger factors have actually been around since like the 30s, but if you actually go through and do the full-blown 3D FEA, break out the FE map or the abacus or the ANSYS and actually compute the stresses, and I'll show you some of those stress distributions on Monday and you'll see what I mean. But if you actually compare those to what's going on with this prediction is remarkably simple and accurate enough for engineering applications. And there's going to be a lot of those, not just in other courses, but in this course. So just be aware of that, okay? In fact, we're going to deal with some more of them on Monday. Okay, now one other note on stagger factors. I want to make sure that everybody's clear on this. Let's take a look at this connection, okay? So I want to take a look at this connection, and I want to look at this path. Okay, so if I was trying to look at this formula right here, I would say the gross area minus how many bolts? How many bolts would I subtract from that path?
4. Well, yeah, 4.
Well, 4 or is it 5?
I miscounted 5.
5. No, that's fine, that's fine. So the gross area minus 5 bolt holes. How many stagger factors do you have? The question is, let me ask you another way. Do you have one big stagger factor or 4 tiny stagger factors? The answer is you use 4 tiny stagger factors. The stagger factor expression is S squared over 4G, right? So mathematically, you can't just use one big S value and get the same effect as 4 little s values. It doesn't work that way because it's quadratic, okay? So in this expression, you'd have the gross area minus 5 bolt holes plus 4 stagger factors. Yes?
So can you just do the stagger factor once and then multiply it by 4?
If the distances are the same, yes.
Okay.
Absolutely. If the distances are not the same, you will have separate stagger factors. Questions? All right, so here's a more complete expression for AG. For AN. I propose that the net area can be computed as the gross area minus the area lost due to the presence of bolt holes plus any necessary stagger factors. And that's basically what I have here. So if you want a starred slide to put in your notes or what have you, this is it. Now, one of the things that I have actually kind of glossed over, but it's actually really simple to deal with, is this formula is the net area expression for bolted connections. I kind of just ignored welded connections, didn't I? What is the net area for a welded connection? Well, for most welded connections, you're not actually removing any material to weld it. You have an angle, you have a plate, stick the angle on the plate, weld it, right? Fillet welds. Arguably the most common type of weld we see in structural engineering applications. Because you're not removing any material, what is the net area? It's the gross area, right? So there's no real math that you need to do. And if there is material removed, just account for it. It's just geometry, okay? What do we think? So far, so good? Would you like to do some problems instead of me just sitting here yapping along? Let's look at this. So let's compute the net area for this plate, okay? So the plate is 1 inch thick. I'm using 3/4 inch diameter bolts. And let's take a look here at my dimensions. I've got a plate that's got 1.5 inches. Now, here's something I put here. 1.5 inches, and I'm using this TYP. TYP stands for typical. It's just a means of reducing the clutter on these schematics. So if you see that, that's what that means. So it typically means that those dimensions repeat. over and over again for a given problem. 2.5, 3.5, 3.5, 2.5. So what's the total width of this plate? 2.5 and 3.5 is 6, so 12, right? I get that right? Okay. All right, let's bring out the notebook. Let's do some math. Is our recording still going? Yes, it is. I hope it's working, so. All right. Come on. Okay, so our expression that we're now utilizing is AG minus that plus the sum of stagger factors. And then stagger factors are S squared T over 4G. So that's sort of the governing equation, if you will, that we're utilizing for this problem. Okay? So, is there anything that I can compute right now in this expression? Well, do I know, can I compute the gross area? What is the gross area for this plate? Say it again.
12 inches squared.
That's exactly right. That's not too bad, is it? Not too bad? Okay. I don't know about you, but we got a lot going on with in this expression. So let's see, what do we got? We got the gross area. We know the thickness. What about the effective hole diameter? Can we deal with that? Yeah. If the bolt diameter is 3/4 of an inch, what's the hole diameter? 7/8. And you get that by doing what again? Remind me? Add 1/8 of an inch. So here, I'll write it out. Write my governing equations. These are system parameters, aren't they? Okay, now, I am going to put some letters, if you will, on this. So, let's see, A, B, C, D, E, F, G. Help me out. What are our possible failure paths? Somebody help me out with naming these. ADF. All right. Give me another one. Somebody else.
B, C, D, F.
All right. All right. What would you say again?
B, C, D, E, G.
B, C, D, E, G. Okay. Is that the one you said? Who was it that said the other one? Okay. Hold on. I can do better than that. So there's B, C, D, E, G. Is there any others?
BCBF.
B, C, D, F, but is that mirrored? Yes, it is. And what's its mirror?
GEBA.
We'll do it alphabetically, but you're right. A, D, E, G. You're 100% right. Now, I would argue that the only remaining challenge is to look at our stagger factors. What is S going to be for these diagonal bolt paths? 1.5, right? It is 1.5 because I'm yanking on the member like this, okay? So here's the member, here's the break line. I'm going to yank on it like that, right? So the distance along the x-axis is my pitch, right? That's this distance here. And so that's going to be 1.5 inches. Oh, hold on. And if that's 1.5 inches, what is this one? 3.5 inches, because that's this distance here and that distance there. And if that's 3.5 inches, what's that? That one's easy. That's just the thickness. What's the plate thickness? 1 inch. Okay. Is everybody with me so far? So, here's our possible failure paths. Okay? I'm going to compute all of them. And you're going to see a pattern here, but just humor me for a little bit. Let me scroll up a little bit. Let's talk about path ADF. What is the formula? Here's the formula. I take the gross area minus the area lost due to the presence of bolt holes. How many bolt holes are along path ADF? 1. Okay, so maybe we'll do this. Okay, so let's just conceptualize this just to see if we're on the same page. That marker's done. Where'd my other marker go? Ah, here it is. So, we take the gross area minus 1 area of a hole plus how many stagger factors? For path ADF? None, right? That's 0. So this first path here is just that. So it's and so I think I can do that one in my head. That's going to be something like 11.125 inches squared. Is that right? Is that okay? Now what about this path, this second path? Okay, this second path is BCDEG. So BCDEG, how many bolt holes am I going to subtract? Now are we going to add stagger factors for that path? How many are we going to add? That's exactly right. Does that make sense? So for path 2, Is that fair? The way I've got this written? The gross area minus 3 bolt holes plus 2 stagger factors, right? So, what do we got? Equals I already hear the familiar sounds of Casio FX115 ES pluses or similar scientific calculators being broken out of bags and whatnot. Oh, I forgot a parenthesis. Oops. Anybody got an answer for me? We'll say like, I don't know, 3 decimal places.
9.696.
9.696. Do I have a second on that?
Yeah.
All right. So, what's the formula going to be like for the third one? For the third group? So, we're going to take the gross area minus what? So, it's BCDF. All right, so here's the connection. How many bolt holes are we subtracting for BCDF? Plus, how many stagger factors? So, so what does this one yield? 10.411. Do I have a second on that? Okay. So, now I'm confused. I'm going to need your help. So, the purpose of this problem was to compute the net area. Well, I don't have a net area. I got 3 net areas. Which one do we use? The smallest. Why do we use the smallest? Well, if I'm taking this member and I'm yanking on it, its capacity is a function of its area. The bigger the area, the more it can hold up. So on the flip side, if I'm taking this and I yank on it, when is it going to fail? It's going to fail under the path with the least area. Okay? Does that make sense? Now, I'm going to throw some structural engineering jargon at you right now. We're going to say that this value governs. And what that means is that of these values, that is the value that dictates the rest of our computations and the rest of our design. Okay? And that concept of one value governing over others or one limit state governing over others is incredibly important in the land of structural engineering. For example, when we're looking at tension members, we're going to have scenarios where we have multiple limit states. We have gross section yielding, we have net section fracture, we have block shear rupture, we have the bolt capacities, bolt bearing, bolt shear, etc. They're not all going to have the same capacity. One of them is going to be lower than all the others. And so that's the one that's going to govern our behavior. So for example, the member in question for this problem, there's half a dozen different ways that member could fail. But let's say the limit state with the lowest capacity is the bolt shear limit state. So what that means is if I yank on that, that's what's going to snap first. The bolts are going to snap in half. So that limit is what governs the design. Does that make sense? Okay. So first off, to sort of close the example, the question is, what's the net area? That's the net area. Does that make sense? Now, I want to address a couple of points and then we're going to call it for the day. First, for the mathematical purists in the room. How many of you saw in advance that path 3 wasn't going to go? How many of you saw that based on the numbers that, here was a value, here was a value, that this wasn't going to be smaller than these two? Did anybody see that just based on the math? Some of you might have, okay? And there might be a tendency when you're first starting to do this, and this is especially going to be true on this homework assignment that I'm giving you today, due Monday, that the connection in general is going to have like 6 or 7 different paths. And you're going to notice a pattern. You're going to notice it. You're going to go, I know which one's going to govern. I want you to check them all, okay? And I know that some of you are going to go, but come on, that's getting a little ridiculous. There is a reason, okay? Here's the reason, okay? I'll give you an example, a real-world example of a member where you need to check all the paths. We're probably going to look at a member like this a little later in the semester, but this is an angle where there are staggered bolt arrangements and the stagger crosses one leg to another, okay? Now, the way that we handle this is we take this, we break out our secret weapon of structural engineering, the samurai sword or the lightsaber if you happen to be a sci-fi fan, and we turn this into a big old equivalent plate. And so we put that little nub down here, we have this, and now we have a staggered connection. But this distance and this distance are not the same. They're different, okay? They're different because of the geometry, because you're turning that angle into a plate, okay? So in that instance, you can't really use the logic of, well, I know this is going to govern, or I know that this isn't going to be the case. No, you have to actually check all the paths because it's not as apparent as it might be for this plate. So on this homework assignment that I'm going to give you that's due Monday, I am going to see if you can identify all of the potential failure paths. And there's actually quite a few of them. Some of them repeat or are mirrored, so I'll give you that. But I think that there's like 12 different potential paths for this problem. Again, a lot of them repeat, so don't let that scare you. And again, a lot of the calculations are pretty repetitive. What might be valuable is to compute a stagger factor, compute a whole area, and just keep using it over and over again. What do you think? Yes, sir.
So I guess what I need to ask is, like in this case, the stagger factor seemed like it had a much smaller role on the overall, like, area. Is that true in general, or is that something that, like in the case on the board, that's not really true?
That's a great question, and the way I would answer it is the stagger factor is a function of the dimensions, right? So put it like this. If I was a designer and I was looking at this problem and I go, the stagger isn't having as much of an impact as I want it to. Maybe take that 1.5 inches and make it 2 inches. Make it 3. You see what I mean? Now, we start to get into a little bit of a discussion with economy in that regard. Because here's the thing. Let's say I take that 1.5 inches and I make it 4 inches. Well, that's taking a connection that's this big, making it this big. And now I have to make the plate that it's connecting to that big as well, right? So where's the trade-off on what's, more expensive or what, you know what I mean? So it's not that simple. I can't give you a definitive, well, just up it, You have to look at the loads, look at your connection scenario, look at your project constraints, and lay it out to get the best bang for your buck. So this is just another tool in your belt. So make sense? That's all I got, everybody. I will see you all on Monday. Y'all have a wonderful weekend. Try and stay